All right, we're going to wrap up section 3.2 today. Yesterday we talked about range, a very basic level of a measurement of spread. Variation just means that, measure of spread, okay? Today we'll get into variance and standard deviation. All right, we kind of left off talking about the differences here, even though they have the same range. Okay, so yeah, like we said, they have the same range, but these ones are closer to the mean. All right, so there's going to be a calculation for that, and it's called the standard deviation and variance. So here we go. So it does just that. It gives us the measure of the spread of data around an expected value, which is going to be the mean. Okay. All right, now they take us through kind of a pretty elaborate explanation here on page 105. So I'm going to reference that here, how we actually get to this final calculation of the sample standard deviation. We usually call it sample. There is a population standard deviation, which we'll get to next, but typically we sample from the population and we compute that. So this one's more applicable than the population standard deviation. All right. Okay, so here's kind of the procedure, but once I take you through the table, it won't be as intimidating. This kind of looks rough right now, but if you get stuck in any of the steps, this is a good resource for you. We got to start by finding the mean, because that's what the standard deviation is. It's the distance away from the mean of the data set. So we'll find the average. All right, and then we're going to find the difference between each of the individual x values and the mean. That's called a deviation. That phrase, deviation, basically just means distance from the x value to the mean. Okay? All right, and we'll talk about why we have to do this when we set up the table. But all the deviations, some will be like +5, some will be negative numbers. So if we just added up the deviations, they'd cancel and we'd have 0. All right, so that's why we actually have to square them to make them positive, and that way they won't cancel each other out. So we square the deviations and add them up, and then we just apply the formula. That's basically what this last part is saying. All right, so a good resource to go back and review if a step is confusing you. They break it down step by step, okay? All right, so here's our formulas. The variance, notice the difference here between these two formulas. The variance is just the inside of this, right? This is the square root of the sum of squared deviations divided by n minus 1. And the variance is the same thing, just without the square roots. This one is the one we use more often, okay? All right, so you may want to add this here. I kind of... just so you can make some sense. That's very important that you can interpret standard deviation. And the word deviation just means distance from the mean. Okay, so when they say standard deviation, it's kind of like an average. What's the typical distance from the mean? Average distance are all the x values from the mean. That's what it finds. Okay. The most used measure of spread. All right, so I'm going to walk you through here how we do and calculate the sample standard deviation. There's a defining formula and then something called a computational formula. We're just going to do the defining formula. We don't need two formulas to define the same thing. We'll just stick with one. Okay, so here we go. Here's the data set. We've got a random sample of blossoms, and here's the diameters of these mature peak blooms. Okay, so these are going to be in inches. So 2 inches, 3 inches, and so on in diameter. All right, so use the defining formula for sample variance. You might want to write it here because it's on the previous page. That way it's right here and we can access it a little bit easier. So it's S squared is the symbol we use for sample variance. S squared equals, remember, sigma means sum. So sum of these squared deviations. And then once we have that, we just divide by n minus 1. Okay, sample standard deviation. Now we just use the symbol lowercase s for this. And it's everything the variance was, just the square root over top of it. All right, pause and give you a chance to write that down. Okay. All right, so what we want to do now is help organize finding the sum of squared deviations. That's the process that takes the longest. I mean, it's not tough math. We just got to get it organized. All right, so what I want you to do first is let's list our data values over here. So I've got 2 inches, 3 inches, 3 inches. These are the blossoms, right? 8, 10, and 10. So list each individual X value. Okay. All right, now this means that this column right here is the deviations. What's the X value? What's the distance from this X value to the mean? Well, we need to go calculate the mean then. All right, so what is X bar? X bar is going to be equal to our sum divided by 1, 2, 3, 4, 5, 6, right? So I'm going to pause while I'm calculating this for us. Okay, so the sum of those values is 36 inches divided by 6. We have 6 inches for the average diameter of these blossoms. All right, so what I'm doing here is here, I'll just show you the work. You don't necessarily have to do this once you get it going, but 2 minus the mean of 6 is -4. Next deviation, 3 is a little closer to the mean, right? So we'd expect a smaller deviation. The negative just means it's below the mean, and eventually we'll get to positives. So 3 minus 6 is my next deviation. 8 minus 6 is +2. 10 minus 6, +4, and then we have another +4. So these are my deviations. And now you can really see why we don't just add up these to represent a standard deviation. Otherwise, they cancel out. Okay? So part of this process is to square them, and then at the very end, square root it again to get back to an average deviation. All right, so now we just take these numbers and quickly square them. 16, 9, 9, 4, 16, 16. Okay? All right, and let's go ahead and total. You probably want to put a little line here, and let's add these squared deviations up. So I'm going to use this sum. Use all the fancy notation here. And then we just got to go to the calculator and add these up. Okay, I have it here. It's actually from the book, so we get 70 when we total those. Okay, so now we're ready to find the variance and the standard deviation. So the variance, S squared, is equal to the sum of square deviations. We have it now. It's 70. So that's why that table is very handy to get that data value. And then divided by the sample size minus 1. So what do we have? 6, right? So we have 6 minus 1, or just 5. So 70 divided by 5 will give us our variance. So it's 14. Now, right now, it's in units squared. It's inches squared, which doesn't really make sense for a diameter. And it's why we don't actually use variance a whole lot to describe spread. It's just a stepping stone to get us to the standard deviation. Okay, standard deviation is just the square root of everything we just did. So S will be equal to the square root of 14. And we take the square root of 14, we get 3.74 inches. Okay, so what did we just find? Well, look at this data set, right? They're not all right on the mean of 6. Actually, none of them were the mean of 6. Sometimes it was off by 2, sometimes it was off by 4. It describes that typical deviation from the mean of 6. So let's write that down. The typical blossom was 3.74 inches. Yikes, didn't spell that right. Good. 3.74 inches from the mean of 6 inches. Okay. It's kind of like an average distance from the mean. That's why they call it standard deviation, typical deviation. Okay. Sometimes I may ask you to interpret that, and that's kind of what you'd say in your own words. It's the typical distance from the mean. Okay. So here's all the answers: variance, standard deviation, and then a little interpretation. Okay. Okay, don't worry, you don't have to memorize these formulas. The authors also give you another formula called the computational formula. We don't really need it. The defining formula is enough. Okay, so that's all we're going to use. So in your notes, I didn't catch that before. You might just want to cross that out. We're going to use the defining formula, and it's your turn. let's give this a try. I want you to pause the video, create this table, go through and find the variance and standard deviation. Okay. Okay, here's the table. Had the same average diameter, 6 inches. Here's your deviations, much smaller this time. These deviations are much smaller magnitude than up there. So naturally, the square deviations are smaller, and so is the variance and the standard deviation. So we end up with 1.26 inches is the typical deviation from the middle. Okay, and that's kind of our next discussion. They had the same middle, but the data sets look much different. That's actually some of the problems they might give you on a test or quiz or SAT question. They say this data set and this data set has the same mean without even calculating it, which one has the higher standard deviation. Well, if you understand the concept of standard deviation, you understand. Look at how more spread out these data values are compared to these if you know it has the same mean. Okay, so that's part of the discussion on the next page. So go ahead and turn the page and read to yourself the next few paragraphs. All right, so in the explanation, they use the word consistent. That's a good way to think of standard deviation as well. Let me give you a sports example, like a basketball team. If a basketball team is good at shooting threes, or they shoot a lot of threes, they're going to have nights where they're really high on points, and they're going to have nights where they're really down on points. So their standard deviation from game to game of points per game is going to be up and down. It might be a roller coaster ride. They might not be as consistent as a team that shoots inside the paint, and their scores are going to be more consistent. Okay, so in some ways, the standard deviation is also a measure of consistency. Okay. All right, go ahead and read this to wrap it up, and then we'll do one more problem. All right, so the population mean and population variance just means if you have all your data set. If I grab a sample of blossoms, we'd use S. If I have all the blossoms for the Rose Parade, which would be tough to do, then we would actually we'd call it a population parameter. So we'd find the population standard deviation. Notice the only difference in this is instead of dividing by n minus 1, it's n, the actual sample size. But everything else is the same. Data value minus the mean. Okay? All right. So to wrap this up, I want you to use this space, and we're going to complete page 115, number 5, in the space provided. All right, let me give you a little heads up on what they're asking, though, too, once we get there. We're asked to find the range here, compute the sample standard deviation, and then you're going to compute the population standard deviation. You shouldn't need to do 2 separate charts. All you're going to need is one because it's the same data set, but in the end, the formula is going to be slightly different, okay? So go ahead, do number 5 so we can compare the difference of those two, and then I'll give you feedback on that. All right, so here we go. So x minus x bar or x minus mu, it's still going to be the same deviation. So x minus the mean squared is 10 for our sum. Okay, so the range is going to be 6 minus 2, max minus min. So we have a range of 4. Part B was the sample standard deviation. So it was that sum of 10 divided by 4. And then take the square root, 1.58. The idea of the population standard deviation is now you just divide by n. It makes it smaller. That's always going to be the case. The idea is if you have all the data from the population, it's less variable. It's more consistent. Your data is, but don't worry so much about that. You just got to know that's slightly different formula, okay? And different symbol for population standard deviation. All right, that's it for today's lesson.